All right. So the last thing I wanted to talk about was basically what happens in X-rays. Now, like I said, this is how we're able to look at stuff like the structure of atoms or the structure of materials. So materials are often crystalline, and crystalline just means that their atoms are in a nice ordered array. They might not be this ordered, but they are quite ordered. And people learned about 100 years ago, about 120 years ago at this point, I guess, that if you shine light on these guys, what's going to happen is, some of the light will hit, let's say, this guy, and then some of the light will hit that guy, and they'll come out, you'll get some interference patterns, right? You'll get an interference pattern sort of like that, right? So this is, call that theta, and this is 0, and this is your intensity. Basically, the setup looks like this: is you have a laser or something, or an X-ray source actually, because it's usually called X-ray diffraction, but you can do it with light. Most undergraduate laboratories do it with light if they do one. And then, your signal comes back out this way, and basically you come through and you change all the angles. But what happens is you have your detector over here, and this is your angle theta, and this is your another angle theta, and you look at this intensity diagram, and as you go around, you see something like that. When you see something like that, you can figure out what the spacing is, right? So if you look at these peaks, so this would be peak 0, 1, 2, and you can look at these peaks as they go along, what you get is peak number n times lambda is equal to twice the lattice spacing. So this is called the lattice spacing, d. Usually it's a, but for us it's going to be d, and multiply that by the sine of theta. And that gives you, right, this is number 1, 2, 3, and so on, times the wavelength of the light coming in. This is theta here, and then you can use this to figure out the lattice spacing. In fact, you can be really clever, and you can end up getting interesting 2D plots like this. And the intensity goes down and stuff like that. And you'll look at a plot like that, and you can look at this plot, and we're not going to teach you how to interpret it, but you can look at a plot like this and figure out from all of the symmetries, the way this looks, what's actually going on in this material. How are the materials laid out? Right? The materials can be laid out in sort of a square pattern like this, actually a cubic pattern. There are a couple of them called simple cubic, that's rare. Another one called face-centered cubic, where you end up with your lattice looking like this. There's another one that's really important that's called like hexagonal, which means you end up with hexagons. Again, got that one in the center like that. It's not called triangular because there are other things that are going on, so we'd have to talk about all of the reasons why it's hexagonal and not, but you end up with hexagons like that. Here you have squares, and these are how you build up a material from atoms in these different ordered arrays. So you can figure that out from these patterns here. This is probably enough to get us the thing we want, which is the lattice spacing, this distance between atoms here. Right? And that's good enough for a lot of things. I spent a lot of time working with just lattice spacings. So what we're going to say is scattering light off of crystals allows you determine crystal structure. And for us, getting the lattice spacing is enough. All that other stuff with XRD, it's really, really interesting if you're going to go into chemistry or something like that, but it gets a little bit complicated. All right, so you know, there are lots of different crystal forms. You have to be able to figure out how each one works. You have to be able to interpret this plot here, and that takes a lot of time. And so we're not going to get to that. But just understanding that, you know, you get wave interference from these two slightly offset light beams, right? The beam comes in here, some of the light bounces off, some of it bounces off the next layer. Actually, some of it bounces off the layer after that, and some of it bounces off the layer after that. But it gets less and less and less for each time because it keeps losing intensity every time it goes through a layer of atoms. And that gives us a nice pattern there that tells us something about the material. Which I love, actually. That's really cool. This is how they figure out how big things are. So if you're doing something like nanotechnology, you don't have, if you want to figure out how big your object is, you can't really use a picture. You can kind of use a picture. You can use like a scanning electron microscope. The scanning electron microscope, you still need to do this. You still have to use the diffraction pattern. In that case, it'll be an electron diffraction pattern to calibrate the size of your object. Right. So the sizes that you're measuring are all based on these diffraction patterns. So it's really important and really cool, and has to do with all sorts of high-tech stuff. All right. Right on.